an interesting work. With an application of reinforcement learning to an energy problem. So Bianca, she's currently doing her PhD, third-year PhD at INRIA in Grenoble. She's present visiting professor in the university at the Polytechnic in the university in Milan, actually. And then, so I think we don't have much time. I would like you, Bianca, thanks for accepting the invitation, and I leave you time for your presentation. Thank you very much.
Okay, thank you so much for the invitation. So I'll be presenting today a little bit of my work of my PhD that I'm calling here Convex Reinforcement Learning and Applications to Energy Management Problems. That it's a joint work with my advisors, Margot Bregère and Nadia Odjeune from EDF and Pierre Gaillard from INRIA Grenoble. So I'll first start actually with the motivation of this problem, how we ended up actually studying convex reinforcement learning. So it comes, so this motivation comes from the energy management problem. And then I will talk a little bit more about the mathematical aspects of convex reinforcement learning and a little bit of the work we did. So EDF is an energy company in France that is responsible for producing energy and selling energy to customers. And for a company such as EDF, it's very important to always maintain the balance between the energy that is being produced and the demand for energy at all times. Nowadays, the current solution that is implemented usually is to forecast energy demand and to try to adapt the production accordingly. However, this is super hard, especially nowadays with the integration of renewables to the system, because the sun, the wind, they have an intermittent nature and they are really hard to control. So a solution to this is what we call demand-side management, where instead of trying to control the production of energy, we are going to try to control the consumption of the energy. And this can be done also in several ways. A very common way is to send incentive signals to consumers to try to make them shift their consumptions from peak hours to off-peak hours. And another way of doing this is by controlling what we call flexible devices. And that's what a little bit of my PhD was about. So flexible devices is what we call thermostatically controlled loads that are any type of electrical heating or cooling elements that are controlled by a thermostat. So this can be water heaters, air conditioners, refrigerators, and etc. And we call them flexible because the only thing that matters is that their temperature should be always inside a certain interval of temperature. But besides that, there is a lot of flexibility on how they should be consuming or not energy. And nowadays, with the new technologies of smart meters, we can actually control these elements because nowadays we have almost near real-time communication between the loads and the suppliers. So the goal here, the problem that I was faced with in the beginning of my PhD is how can I control a large population of electrical devices? So to explain a little bit more this problem, I'm going to give the example of a large population of water heaters. So suppose that I have here a large population of water heaters that I'm given here by these M water heaters. And I can look at their individual consumptions at discretized time steps. For example, let's discretize a day in small time steps. And I can look at their individual consumptions that here I'm going to be denoting by this variable on. And just to be simple, I'm going to assume that if my heater is consuming, then on is going to be equal to 1. And if my heater is not consuming, then this variable is going to be equal to 0. And I'm interested in looking at their average consumption. And my goal is actually to compute some sort of control signal that I'm going to be denoting here by pi n at each time step to send to all of my devices. And this is going to induce a certain consumption. And I want this consumption to be this average consumption that this control signal is going to induce to be as close as possible to some reference consumption profile gamma. So for example, this reference consumption profile can be a part of what I'm predicting the energy production is going to be in a certain day. So my goal here is to find a control signal pi to send to my water heaters that you make their consume such that their average consumption is as close as possible to this reference consumption profile. So to do this, we first need to understand what are the dynamics of a water heater today and how can we actually add a control signal to them. So for that, I'm going to explain how a water heater works today without any type of control. So a water heater has the cyclical dynamics where, as I mentioned before, the only thing that matters is that its inner temperature should always be inside a certain temperature interval. And the idea is that if this heater is on, then it's going to be heating water. So the temperature of the water is going to increase until it reaches a maximum temperature. And the moment it does, the heater turns off, and then the water starts losing its temperature until it reaches a minimum temperature, and then the water heater turns on again, and the cycle keeps going. We do have here some change of slope sometimes. That's what I'm calling a drain. So whenever someone is gonna take a shower or wash the dishes, this is gonna drain hot water from your water heater, and this is gonna make the temperature drop faster. So for example, it can happen that this temperature is gonna drop way below the minimum temperature, but whenever it does, you just imagine that the water heater turns on again and the cycle keeps going. So the idea, as I said, is to add some sort of control into the system, because I want to control the average consumption of my population. So the idea is that I want to exploit the flexibility of the problem. That is, I don't care what is my temperature, I just care that it is inside of this temperature interval. So my idea is, instead of waiting for my temperature to reach the maxima or the minima to turn, I'm gonna add a certain probability to turn on or off in between. And to do this, I'm gonna formulate my problem as a Markov decision process, where each one of my agents is gonna be a water heater. And this water heater can have a certain state that tells me if this heater is consuming or not, and its temperature. And this heater can take an action that is to turn on or off, or to keep on or off. And this action is gonna be chosen by following a certain policy that is given by this pi n, that is actually the control signal that I will want to learn in the future, that tells me what is the probability that a certain action is gonna be taken given the current state of my water heater. And then my water heater is gonna move to a next state following a probability transition kernel that I'm gonna be denoting here by Pn, that is conditioned on the current state and action of my water heater. And you just imagine that all of the probabilities of someone taking a shower or washing the dishes, they are all included in this dynamics. So okay, now we have a model for how we can control a water heater. So with this, we can actually write what is the optimization problem that we are interested in solving. So as I said, I have my population of M water heaters, and my goal is now to find a policy pi that is gonna minimize this quadratic loss for each time step between the average consumption of my water heaters and this reference consumption profile. However, we can imagine that I want to control a very large population of water heaters, for example, for a whole city. And I can assume that I'm looking at a homogeneous population where every one of these water heaters is going to be following the same dynamics, P, and they are also going to be following the same control signal pi. So I can actually take the mean field limit of this problem, and instead of considering a finite population, I'm going to consider an infinite population. And by doing this, I can actually start looking at this variable here that I'm calling mu pi p, that tells me the state action distribution of my water heaters. So this variable here is going to tell me what is the probability that a water heater is in a certain state and taking a certain action, given that it's following the control pi in the MDP that has the dynamics given by this probability transition kernel. So instead of looking at the average consumption for a finite number of water heaters, I can see this average consumption as being the expectation of the variable that tells me if my heater is consuming or not, where this expectation is taken with respect to the state action distribution. And this allows me to actually write the control problem that I'm actually interested in solving. That is to minimize, here I'm writing a function f that is a quadratic function, but we can imagine that this function f can be really general. But for my problem, here is a quadratic function. Though this problem is to minimize this quadratic function and find a policy that is going to induce this average consumption such that it's going to be as close as possible to this reference profile. So, okay, this is the optimization problem we have. And as I said, for this demand side management energy problem you're facing, this function f is quadratic. But we can actually also be interested in a more general way of phrasing this problem, where we are going to consider any sort of convex function. So here's the problem of just finding a policy pi minimizing any convex function with respect to the state action distribution being induced by this policy pi. And this is what in the literature, a lot of people call the convex reinforcement learning problem or the concave utility reinforcement learning problem. So what is the link with reinforcement learning here? So in reinforcement learning, we also have a Markov decision process where we have an agent that has a certain state and you take an action following a certain policy, and then it's going to move to a next state following a certain probability transition dynamics. And this agent, at every time step, it suffers a loss that is given by this Ln that depends, it's a loss that depends on the state and the action that my agent is passing at each time step. And the goal of the reinforcement learning problem is to find a policy pi that minimizes the expected sum of losses. With the state action distribution notation that I introduced before, we can actually rewrite this problem as being a linear problem, the problem of minimizing a linear function on this state action distribution. So actually, when we phrase the reinforcement learning problem this way, we see that we can actually, instead of considering only linear losses, we could also consider any sort of convex loss over my state action distribution. And this is what we call the convex reinforcement learning problem. So as we saw before, the demand side management problem I introduced, it has an f that is a quadratic f. And there are a lot of other problems in the literature that can also be written as this convex RL problem. For example, the problem of pure reinforcement learning exploration, this function f can be the neg entropy, or the problem of imitation learning that is very common in robotics, where the goal is to find a policy that is going to imitate a certain behavior, where this objective function usually is given by some Bregman divergence. So this is really interesting. This is a very broad problem. However, the fact that we have a convex loss and not a linear loss makes that the classical Bellman equations that we usually use to solve the reinforcement learning problem, they are not valid anymore. So all of the algorithms that we know for RL, they do not work anymore for convex RL. So recently in the literature, if we look at this convex reinforcement learning problem in an offline version, so here what I'm calling offline is that I assume that this objective function f is known and the dynamics are also known. We have some works in the literature that have came up with some algorithms to solve this problem. So the first one is this one from Elad Hazan, where he proposes some sort of method inspired by Frank Wolf to solve the pure reinforcement learning exploration problem, that is when f is the neg entropy. We have also another work that is going to solve this problem trying to use policy gradient methods. And more recently, we have this work from Mathieu Geis that is going to actually phrase this problem as being a special case of mean-field gain, and is going to propose mean-field gain algorithms to solve it. So, okay, so this is the offline version of the problem. However, if we start to think back again on the demand-side management problem that I introduced before, where my goal was to compute a policy pi that induces an average consumption that is close as possible to a reference consumption profile, we can actually think that in real life, things are uncertain and we have a lot of non-stationarity. So the goal for an energy enterprise in this case is to do this control in a daily basis. And it might be that because of variations in energy supply and in flexible consumption, that both the dynamics, P, where I have encoded the consumer's consumption behavior, they may be unknown and they may also change every day. And also this reference consumption profile gamma may also change every day and also may be unknown. So in real life, we actually want to consider an online version of this convex reinforcement learning problem, where now the goal is to assume that I have a certain number of episodes, and my goal is to compute actually a sequence of policies, one for each episode, that is going to minimize a total loss, where now I also want to face the challenges of having an objective function that can change every day and may be unknown. And maybe I can also face the challenge of having dynamics that are unknown and that possibly can also be changing every day. Okay, so now I have two forms of writing this convex reinforcement learning problem. So now that I framed this convex reinforcement learning problem, I'm gonna introduce two methods to solve it. So the first one is a method that we introduced to solve the offline version of this problem, that when we consider that the objective function is fixed and the dynamics are also fixed and known. And then I'm gonna generalize this to solve a specific online version of this problem. So let's start with this offline version of the problem. So we have here the problem in the beginning. We want to find a policy pi that minimizes the convex function on the state action distributions. So this function is convex on the state action distributions, but it's not convex on the policy pi. And actually taking the gradient of this function with respect to pi can be kind of hard. So it would be actually nice if we could come up with some sort of sets on the state action distributions such that I could make some sort of equivalence between solving this problem on the policies and solving this problem on the state action distributions. And it ends up that we are able to come up with a certain set. So here I'm introducing the set MP, that is nothing more than the sets of all of the state action distributions that satisfy the dynamics of my Markov decision process. And it ends up that solving this problem, this minimization problem, inside the set of state action distributions is equivalent to solving the problems in the policies. So this is very nice because this problem, the state action distribution, is convex. So I can actually find an optimal state action distribution. There is a way of taking the policy associated with this state action distribution, and then this policy is going to be an optimal one for the initial problem. So this is very nice because now I can actually deal with a convex problem. And by dealing with a convex problem, I can propose nice algorithms. So here we propose an iterative scheme where at each iteration, I'm going to be computing the state action distribution that satisfies Bellman flow, minimizing some sort of linearization of my objective function, where I also add a regularization. So this type of formulation of making an iterative scheme is nothing new. But what is different here is that we are going to be proposing to use a non-standard regularization. So usually when we have these types of optimization problems with regularizations in a space of measures, people are going to use a Kubeck-Leibler divergence. In a Kubeck-Leibler divergence, here in the log, I would have actually the state action distributions. What we are proposing here, instead of having the state action distributions, it's to be comparing the policies in here. So the first reason for this is that actually with this specific regularization, we are able to show that with dynamic programming, we can solve this optimization problem and find a closed form solution for it that is given by this exponential twist here on my policies that depend on an auxiliary Q function here that is very easy to compute. And the idea is that if we had a Kubeck-Leibler divergence, the way that we would have to solve this problem is first, we would need to solve the unconstrained problem, and then we would need to do a projection step. And this projection step usually has no closed form solution, and then you need to have some sort of solver to solve it. So with this nice choice of regularization, we can actually have a closed form solution for my policies. And it ends up that we also have some convergence analysis for this type of algorithm, because it is not trivial, but we are also able to show that this regularization is a Bregman divergence. So in the end of the day, all we are doing is solving a mirror descent iterative scheme. So we can actually just adapt the convergence proof of the classic mirror descent algorithm. Okay, so this is for the offline problem where I assume the objective function is known and the dynamics are also known. Now I'm going to talk about the online convex reinforcement learning problem, where the idea here is that I'm going to have T episodes, and I'm going to assume now that the dynamics, they are not known anymore, but I'm going to assume that they are fixed. But I'm going to assume that the objective functions, they are adversarial. And in online learning, usually when we say adversarial, it means that they can change every day and they are unknown to the learner. So you assume there is an adversary that before the program starts, it's going to choose a sequence of objective functions. And it can choose the sequence of objective functions in an arbitrary way that is unknown to the learner. And the idea here is that we are going to follow an online protocol where at every episode, the agent is going to start in a fixed initial state action distribution. And at every step is the same thing as always. It's going to have a state that follows a certain probability transition. It's going to take an action based on a policy. And then the end of the day, it's going to observe the loss function that it suffered. And we assume that it actually observes the whole objective function. And using the state action trajectory, it's going to estimate its probability. It's going to update its estimate for the probability transition. And using this estimate and the information of the objective function is going to compute the next policy for the next state. So this makes two questions appear. So the first one is, how do we use these trajectories to estimate this probability transition? And the second one is, how do we use this estimate and the objective function to compute the next policy? So the idea here is that, as I know nothing about the environments, I actually want to compute a policy that manages to balance two things, one that I call the exploration and one that I call the exploitation. So if I have a policy that only explores, it's gonna make sure that I'm gonna be passing through all of the state and actions a very good amount of time, which probably is gonna ensure that I'm gonna learn very well the environment. However, it might be that this policy is not optimal because it's gonna pass through a lot of state and actions that maybe are gonna give me a very bad loss. But if I have a policy that only exploits, so if I only play the current optimal policy, it might be that this policy is not gonna pass through some state and actions that I'm never gonna learn the environments on these state and actions. And it might be that actually the true optimal policy would be one that would pass through these ones, and I will never learn it. So the goal here is that I want a policy that manages to balance both things. And the way that I'm gonna measure the performance of my algorithm is by using the static regrets, where I'm gonna be comparing the learner's total loss with that of the best policy in hindsight. So here I'm gonna be comparing the best policy in hindsight, considering all of my episodes. Okay, so to compute these probability estimates, here I'm just gonna give an idea of how we can do this. We can do this in a lot of ways, but there is this result that is quite classic in the literature, where we can just compute it by using the empirical estimates. So we are gonna count how many times the agent visits a couple XA, and how many times that it is in the state XA, and then it moves to a state X prime. And then we are gonna use this to compute the estimation of the probability transition. And then we have some nice concentration results on the quality of the estimate that tells me that it depends, that it is inversely proportional to the square roots of the number of times that I've been to each one of the states and actions. So this is a classic result. And then to compute the policy pi, we can ask ourselves, why don't we just use the same sort of mirror descent iterative scheme we did before for the offline version, where the only thing that we have to do is to use the estimate probability transition because we do not know the true one. The only problem of doing this is that a policy that solves this problem is actually going to be a policy that only exploits, and it's not going to ensure that I'm going to be exploring the environments well enough, and it's not going to ensure that I'm going to be passing through each state and action enough so that I have a nice idea, so that I actually learn well my probability transition. So an idea to actually solve this problem is to define a bonus vector. So I'm going to define a bonus vector that actually also is actually inversely proportional to the square root of the number of times I've been to each state and action. And what I'm going to do is, instead of solving this mirror descent iterative scheme with only the gradient of my objective function, I'm going to add this penalization that is this bonus vector. So the idea is that if I have a state and action that I didn't pass a lot of times, this bonus vector is going to be big. So I'm going to be penalizing a lot this to ensure that I'm actually going to have to force my policy to pass through this state and action. And if I have a state and action that I've passed a lot of times, then this bonus is going to be small and the penalization is not going to be super big. And we actually managed to show that by doing this, we can show that with high probability, we do manage to have a sublinear regrets of the order of square root of t. So this is just some of the, these are just other parameters of the Markov decision process. So this is the Lipschitz constants of the objective function. Here is the size of each episode, the size of the state space, and the size of the action space. And being in paying the square root of t is actually, this is a lower bound too for the problem of reinforcement learning in this scenario. So, okay, this is really nice. I showed two algorithms, one for the offline problem, one for the online problem. So now, just to conclude, going back to the original problem in the beginning, I just wanted to show a small experiment about how we applied all of this to the water heater problem that I mentioned in the beginning. So as I said, the problem is that we had in the beginning to find this policy pi such that this is going to induce an average consumption that is going to be as close as possible to a target, to a consumption profile targets. So the way that usually in experiments we build these targets is that we first take the average consumption of my water heater population in a day, and I add some sort of deviation. So here, for example, I want to make this my consumption be smaller in peak hours, and then they can compensate on the times that they are not consuming a lot. And for the experiments that I'm showing here, I'm going to be considering 10,000 water heaters, a time horizon of 1 day, and I'm discretizing time steps every 10 minutes. And here the idea is that here I'm running this MD curl, that is the algorithm that I explained about offline, the offline convex reinforcement learning one, for the quadratic function that I showed. And I'm comparing here with the fictitious play algorithm from Infuse Games that also work for this problem. And we see here, first of all, that our target is this red line in here, that is the nominal consumption in purple plus the deviation. And first, we see that both the mirror descent algorithm and the fictitious play, they manage to follow really well the targets. And we can also see the objective function, and we see that mirror descent usually outperforms fictitious play in terms of speed of conversions. So if you have any more interest on the things that I'm explaining, I'm gonna just drop some references here. So for the offline convex reinforcement learning algorithm, you can find more details in the paper that we published this year at AISTAT. For the online version where we add the bonus function, this is a paper that is under review that soon is gonna be archived. I didn't show this, but this is another project that we also did with online convex reinforcement learning, where now we are we actually tackle the problem of non-stationarity. So assuming that the dynamics, they can also change every day. And this is a result that we're gonna be presenting in NeurIPS this year. And all of the applications to the demand side management problem, they are also in a paper that is under review and that you can find on archive now with all of the experiments. So thank you so much for your attention. And if you have any questions, feel free to ask.
Thank you very much, Bianca.